Previously, we looked at fiber optics, what a fiber optic is, its structure, and the dispersion through a fiber optic, single mode, multi-mode, and now we are looking at what happens to the signal within the fiber optic. That is what we are calling attenuation. Attenuation is the reduction in the intensity of the light pulse as it passes through the fiber optic. And this is because of the processes that actually depend on the wavelength of light as it passes through the fiber optic. Let's look at an experiment. In this experiment, we have the function generator that's generating the sine wave. We have the transmitter, which is converting it, and then we shall have the optical cable whereby light pulse is passed through it and a photo is detected, which is then received, and then the signal is sent to the oscilloscope for display. When we connect the simulation, so we connect the function generator to the transmitter system, which is then connected to the optical cable system, and then later to the receiving system, and finally to the output to display the graph. After connection, we now need to power on the system, so we connect the sine wave and then the oscilloscope. What we are seeing here is the amplitude, the frequency, and then the add button, which helps us add values of the input voltage and the output voltage plus the gain. When we add our first value, we get that, so we can adjust the input signal, and then we have different values. So we shall record the different values and get different data points, and then we shall plot and get a graph. This is the graph we get of attenuation against wavelength. So there's attenuation with wavelength here, what we may call the Rayleigh scattering, and this is a process that leads to the decrease with wavelength, and this is caused by local variations in the refractive index. Then approximately 1200 nanometers and the 1400 nanometers, we have two peaks which are caused by what we call the hydroxyl absorption peaks or points. Then that is because when a fiber optic is being produced, it's never perfect. It always has water remaining in it, and that we call it impurity, and those impurities are causing what we call the hydroxyl ions in the glass structure. So that's why we see those two peaks. Then beyond, or around 1600 nanometers and beyond, is what we call the lattice absorption point, and this is because of the infrared region, which is caused by the energy absorption by lattice vibrations that are of ions that are within the glass material. What we have seen, those are factors that we call inherent, or that come with the material. But then there are also external factors that affect or that lead to attenuation, and some of those are micro bending, loss. Basically, this is the light that is being radiated away from the guiding direction of the fiber optic, and basically caused by the changes in the guide geometry of the fiber optic and the refractive index of the optic. Then there's what we call the macro bending loss. This one is also caused by the changes in the refractive index. However, for this one, it's experienced during its use when the strains are being experienced on the fiber optic. So basically, fundamentally, we shall look at micro bending as one caused by scattering of light, and then this one, the energy lost or the light lost during the extrusion when the material or fiber optic is being used.